So Landau's model is a mean field model. And in the Landau's model, we express the free energy as a constant plus some function of the square of magnetization. This term is temperature dependent. It is bestowed with temperature dependence. And then we have a term that depends upon the fourth power. And only even powers of magnetization are allowed. And this is a mean field model. How can we show that this is a mean field model? Because if we look at the Brillouin function description of the magnetization, in which m equals ms and the Brillouin function of Gj mu b some b, which is b plus lambda m j over kbt. Now if we expand this Brillouin function as this power series in m, we will get an m term and an m cube term and an m raised to the power 5 term. We expanded this. Now if you multiply that m with b, we'll get an energy. So we'll get an m square term and an m4 term, and this we know is a mean field model. Because what is expressed here is that all the spins are seeing a mean field b plus lambda m. So this is a mean field model. So this model is exactly analogous to the Brillouin function model. So the Landau model is also a mean field model. And from this mean field model, we were able to derive certain characteristics of the order parameter. And we found out that the order parameter depended upon temperature in a certain characteristic way. And we were able to write down the critical exponents. For example, we were able to write down m, the heat capacity, the susceptibility, etc. in terms of powers of T minus TCO, Tc minus T. Alright? And we were also able to express m as a function of the mean of the field H. So the Landau model is a mean field model, and this is something we covered in the previous lecture. And it has the ability to describe properties of ferromagnets. Now we would like to introduce more complicated models to describe ferromagnetism. And something that we have overlooked so far in the course is the concept of band magnetism. So the concept of band magnetism is crucial to an understanding of magnetism. We know what magnetism is, but so far we haven't introduced the band picture into the subject, which means that we haven't really looked at why are the elements iron, cobalt, nickel, dysprosium, gadolinium, etc. magnetic. Now these are band magnets. They have free electrons, and these electrons belong to a certain band structure. No doubt, we have seen free electrons in our study of magnetism, and we've seen that these free electrons give rise to polyparamagnetism, and they also give rise to Landau diamagnetism. But these are properties of free electrons. What if those electrons are not free, rather they belong to the valence band, they belong to the atoms? Now, there is no such thing as a totally free electron. The electrons belong to some bands. Those bands could be the valence band, the conduction band. So we really have to look at a more sophisticated treatment of electrons inside metals. And when atoms inside a metal come close together, they form metallic bonds. and a band structure is made. So electrons belonging to those bands, what kind of magnetism do they produce? Now, if you look at iron, for example, BCC iron, in BCC iron, the magnetization per formula unit is 2.2 Bohr magnetons. Now this looks strange. If you look at an iron ion, it's a 3d6 ion. Now for this ion, if we use Hund's rule, we'll find out that the 6 electrons go into the d orbital like this, and we have 4 unpaired electrons. So if these electrons were totally localized, that is, they belong to the respective iron cores, then we should have 4 mu b. 1, 2, 3, 4. The uncompensated spins are 4. So we should really have 4 mu b as the magnetic moment of an iron atom. But now we have 2.2, a non-integer number. Where is this non-integer coming from? Alright. So now these electrons actually belong to a band, and the next 2 or 3 lectures will be spent on describing why are these metals magnetic. Okay? Now the bulk of magnetic materials derive from these 3 elements: ferromagnets, iron, cobalt, and nickel. So you alloy iron with something else, you get steel. You can get carbon steel, you can get different kinds of, you can get stainless steel, which is, you get the magnetic, non-magnetic stainless steel. So most of magnetism revolves around these 3 elements. Gadolinium is a rare earth. These are transition elements. Gadolinium and dysprosium are rare earths. Gadolinium has a Curie point roughly the same as room temperature. So at room temperature, sometimes it's ferromagnetic, sometimes it's paramagnetic. But these 3 form the major thrust of all magnetism. And when we alloy these elements with others, we get more interesting properties. We can increase the hardness, we can increase the corrosion resistance, etc. Now, in order to discuss band magnetism, we also have to talk about bands. And now what we're going to do is, basically, we are trying to introduce interactions, and we would like to see how these interactions lead to magnetism. So we would like to see how magnetism stems out of interactions of different kinds. And I'll give you some simple examples. Then I will talk about bands, and then I will talk about band magnetism. Probably we will not reach these elements today, but we'll at least start talking about interactions and how they cause magnetism. By the way, this subject of band magnetism is also called magnetism due to itinerant electrons. Now, let me give you an example. First of all, of an Ising chain. A finite sized Ising chain or an infinite sized Ising chain. Now I am introducing an interaction. An interaction is of the Ising kind. So if I have 2 spins and they interact in this fashion, minus 2j s I z component of the ith spin, the zth component of the neighboring spin, and we sum up these interactions over all the spins. And this kind of interaction is called an Ising interaction. It's just one term in the Heisenberg exchange interaction. The Heisenberg exchange interaction has a planar Hamiltonian XX, y and z. We're just picking out the z interaction, which means that we really have a chain of spins these spins are separated by a distance a, which is a lattice constant, and it's a 1D chain. So the dimensionality of this system is 1. So it's a 1D chain. And each spin can point up or down because it's just the z component we're talking about. If we take the z axis to be the vertical axis, the spin can point up or it can point down, right? So it's a one-dimensional chain of spins, which means the dimensionality of the system is 1, and the dimensionality associated with the spin, it just can point it in one axis. So the dimensionality associated with spin, let me draw this with D, this is also 1. Okay? So this is an example of an Ising chain. This, we have proposed a certain interaction, and we would like to see whether this interaction can lead to magnetism or not. Can this lead to a ferromagnetic behavior at some temperature? Now this is not a mean field model. In a mean field model, all the spins are seeing an average field. Each spin is seeing an average field. Here, each spin is interacting with its immediate neighbors through a quantum mechanical interaction. So we would like to see whether this spin chain of this dimensionality, both in space, this is a space dimensionality and this is a dimensionality of the spin, or the dimensionality of the order parameter. The magnetization can be up or down. So it's the dimensionality of the order parameter. So this system, which is generally called a 1-1 system, with this represents D, this represents small d. We would like to see whether this interaction inside this chain can lead to magnetism or not. Now this is something easy to observe. If all the spins are parallel to one another, this system will have a certain energy. So the ground state energy when all spins are parallel, J has to be positive if you want to expect ferromagnetism. J is positive. This is the exchange coupling constant. Now if all the spins are parallel, then the energy of this system is going to be minus 2J. Now we would like to find out the eigenvalues of these spins. So this has an eigenvalue 1/2, this has an eigenvalue 1/2. So 1/2 into 1/2, 1/4. And how many pairs do we have? This is over. So this is an interaction between the first and the second. Then we have the interaction between the second and the third. So our I goes from 1 to n minus 1. Okay, so if n is large, I call this m. So I get minus j over 2n. This is the energy of the system. Now suppose I have the same system. Now this is the energy of all spins being parallel. Up or down, it doesn't matter. Now I would like to find out what's the energy of this system if one of this spin misbehaves and goes in the opposite direction. There's a defect, a magnetic defect. Only one out of the n spins points in the opposite direction. Now the energy of the system must go up because there are two energies that are going up. One is this energy and the other is this energy. Both of these interactions are costing energy because the spins are now antiparallel. One of the eigenvalues is positive, the other is negative. You multiply them, you get a negative number, this gives you a positive energy. So there's an energy cost for for a spin pointing in the wrong direction. This sometimes reminds me of genetics, in which a single nucleotide can get mutated, a single nucleotide polymorphism. So it's a single nucleotide polymorphism in a magnetic chain. Now if this spin goes wrong, the extra energy that is costing it is this interaction, which is costing an energy of minus 2j half minus half, which is plus half. And this interaction is also costing this energy. So the energy cost is 2j. So the new energy of the system has gone up. Okay? So the energy with one defect of this chain has gone up, minus j over 2 n. Okay, let's call this n minus 1, doesn't matter, n minus 1. So it's minus j over 2 n minus 1 plus 2j. So this becomes minus j n over 2 plus j over 2 plus 2j. So the energy of the system has increased by some amount. Now the question is that if we have one defect inside the system, the energy of the chain goes up. So the favorable situation, the ground state should be this state. So ferromagnetism should be allowed. This is what appears at the outset. So just looking at the energy, it appears that this should be the ground state. Ferromagnetism is permitted, is permissible. But there is a counter argument. Can there be a counter argument? Is the energy, this is the internal energy of the system, the magnetic energy of the system. Is energy the only consideration in determining whether you have a stable state or not? Do you have to consider something beyond the internal energy as well? Or is the internal energy sufficient to tell us whether what the equilibrium state of the system is? Is internal energy sufficient? Exactly. Here I have a minus 2j half half, so it's 2j over 4, isn't it? 2j over 4 plus 2j over 4. This is j by 2, j by 2. This is j. So this is actually minus j n by 2 minus j by 2 plus j by 2 plus j. Exactly, Shafia, the internal energy does not alone decide what's the equilibrium state of a system. What has to be minimized is the free energy. Okay? So now U is minimized. The internal energy associated with this configuration is smaller, but that does not alone determine whether this state is to be preferred over this state. We have to consider the free energy, and the free energy is given by U minus Ts. So ferromagnetism dictates that this energy is fluid. However, we have to take into account the entropy of the system as well. Now what's the entropy of this state over here? What's S for this configuration? Statistical mechanics पढ़ा है? What's the multiplicity here? 1. So what's entropy? 0. It's a pure state. This is one macro state. The macro state is all the spins pointing in the same direction. There is only one way in which this can be achieved. So the entropy of this system is 0. There is only one micro state and one macro state associated with this. So the natural log of 1 is 0. So the entropy of this system is 0. The spin entropy of this state is 0. So if you look here, even though u is small, S is also 0. So the free energy for all spins being parallel is just u, because this entropy is 0. Even if you're at 0 kelvins. Now if you look at this configuration, we have to find out the entropy of this configuration. Now what's the entropy of this configuration? The macro state is that there is one defect inside the system. Right? N or n minus 1, right? So the entropy of this system is kb natural log of n. High entropy. This entropy is 0. This is a high entropy state, which means that F is U minus Ts. Now, having one defect increases this energy by some units, by J or J by 2 or some units of J. However, the defect has lowered the entropy by quite a lot, the Kb natural log n. And if n is large, the lowering in entropy is extremely large. So if n goes to infinity, if we have an infinitely long chain which is connected through an Ising interaction, then the entropy of having a defect is really large. In fact, the entropy will also go to natural log of a large number, which is infinity, and f will go to minus infinity, which means that the f will immensely drop if you have defects inside the system. Alright, so the only possibility is that ferromagnetism, that is, you can have a no defect state only when the temperature is 0 Kelvin. Because at 0 Kelvin, this entropy doesn't matter. Which means that this kind of interaction predicts a critical temperature of 0 kelvins. And above 0 kelvins, you cannot have a purely ordered state. So you cannot have a saturated ferromagnet in which all the spins are pointing in one direction for an Ising coupled chain. So this kind of interaction is putting constraints on what is allowed and what is not allowed. You cannot have, in other words, have a ferromagnet. A 1D ferromagnet which is coupled to an Ising interaction is impossible, because you cannot saturate it. You cannot have all the spins aligned in one direction. Okay? So the critical temperature of such a system is 0. However, you can have partial alignment. You can have defects inside the system. That is totally allowed. Now the nice thing is that we can use other tools of statistical mechanics to derive other properties of these chains, which are coupled to a particular kind of interaction. For example, let's determine the heat capacity of an Ising chain, of a finite Ising chain. In other words, in low dimensions, entropy wins the game. In high dimensions, entropy may lose out on the game. You can come up with a similar argument for a 2D Ising chain, in which the energy goes up and the entropy goes down, but the scale at which one goes up is the same as the scale at which one goes down. so the critical temperature can be higher. So in low dimensions, generally entropy wins the game. So when you're discussing low dimensional materials, you have to take into account the role of entropy. Now what we would like to talk about is an Ising chain which is finite and which is periodic. For example, I have a ring of spins and there are n spins on a ring. 1, 2, 3, 4, and so on. And they are coupled through some interaction. Let's suppose we are talking about the Ising interaction. So the Hamiltonian for this system, H, with the interaction that we will introduce is minus 2j, and we are assuming that it is only nearest neighbor interactions. Minus 2j si plus 1, where I goes from 1 to n minus 1. And you also have minus 2j Sn, and these are only the z terms, Snz and S1z. Okay? So this is the complete Hamiltonian for the system. It's periodic, which means that the n minus 1 is connected to the n is connected to the 1 is connected to 2, and so on. It's pairwise interaction and periodic. We have imposed a boundary condition on the interaction, and this is the total Hamiltonian. Now what we would like to do, we introduce a new operator. Let's call it zeta. Zeta I is defined as Siz Si plus 1 z. Okay, so we've just collapsed this into one operator, the Ising operator. Now the eigenvalues of this operator are, of course, they are plus 1 by 4 or minus 1 by 4, because the eigenvalue of each one of them is half. Remember, I am taking h bar equals to 1. Really, there's an denominator, there's an h bar square in the denominator as well. Anyway, I am taking h bar to be equal to 1. So now my Hamiltonian can be written as minus 2j I goes from 1 to n sigma I. Now let's consider just one pair, any pair, k and k minus 1. Let's just consider this pair here, any pair inside this thing. Now what we would like to do is, we would like to write down the partition function z for this pair. For that we need to know the possible energies of the system. Now if you look at this interaction, if you just take 2 I and I plus 1, if you take the interaction between just two spins, it's minus 2j I. So the eigenvalues E, they can be minus 2j into 1 by 4 or into 1 minus 1 by 4. So plus minus j by 2. These are the possible energies of this interaction. Both spins could be parallel, which is lower energy. Both spins could be anti-parallel, which is higher energy. Now we can write the partition function for this pair, because we know the two energy states. One is the ground state, the other is the excited state. It's just like a two levels spin system. Spin could be up or down. Now we have two spins interacting to an Ising interaction. We would like to write down the partition function for this. So what's the partition function? for this pair, for one pair. Exponent e power minus b j by 2 plus this is the partition function. So now this is 2 times cosine of beta j by 2. Remember, our beta is 1 over kBt. So this is the partition function for each pair. Now we can form n pairs, n non-overlapping pairs inside this ring. We can, for example, form this pair, we can form this pair, this pair, this pair, right? So we can form these pairs. So we have n pairs. So when we have n pairs, can we find out the partition function of the total system? Can we write this in terms of Z1? Z1 to the power n if they are distinguishable. So now these pairs are distinguishable. They are all different from one another because they are on different locations. Okay? So we have Zn equals Z1 raised to power n. Okay? So this is just 2 raised to power n cosine n power bj by 2. Now we have the partition function. We can derive all thermodynamical properties from this. For example, we can derive the internal energy of the system. The internal energy of the system is minus d by dB of natural log of the partition function. Okay, this is what we learn in statistical mechanics. We find out the internal energy. This is minus d by dB d beta natural log of 2 raised to power n cosine of n bj by 2. This is minus n d by dB of natural log of 2 cosine of bj by 2. This is minus n 2 cosine of bj by 2, and then we would like to write down the derivative of this, which is 2 sinh of bj by 2 into j by 2. This is minus nj by 2 tan of bj by 2. So we have found out the total internal energy of the system. And now we can find out the heat capacity of this system, which is just the derivative of the internal energy with respect to temperature, or minus kBT okay, I don't remember the other formula. Otherwise, you can just differentiate this with respect to temperature. By the way, if I were to plot versus beta which is proportional to 1 over temperature, the energy of the system, I will get this negative of the tan function. This will look like this. Tan function looks like this. So as I make the system cooler, as the temperature goes down, beta goes up, the energy of the system goes down. Eventually, at large enough beta, I get minus nj by 2, which should be the same energy as I write over here, right? For n, right? This is the same energy. So I can treat everything from a statistical mechanics perspective as well. But you can also find an expression for the entropy of this system. Alright, that can also be derived from the partition function. You can derive the free energy of the system. All these thermodynamical properties can originate, they do originate from the partition function. And I can find out the heat capacity of the system. Now, if I were to calculate the heat capacity, for example, I need to differentiate this with respect to temperature. Let me try doing that. This is minus nj by 2, the derivative with respect to temperature of tan j by 2 kBT. Right? I need to find out this derivative. This is something you could do on your own. I can just give you the final result. The final result for the heat capacity, Cv is n j squared kV. Remember, J is the exchange constant. It's not the angular momentum quantum number. 4 beta squared cosine square of beta j by 2. I forgot to bring in my computer today, but if you plot this with respect to temperature, you can plot the heat capacity. And remember, we're talking about the heat capacity associated with the spin degree of freedom. It's the magnetic heat capacity. There is going to be heat capacity associated with the phonon structure of the system as well. This is the heat capacity associated with the free electrons in the system. This is only the heat capacity associated with the spin degree of freedom, the magnetic heat capacity. And if I were to plot this, I'll get a nice result, which is generally called a Schottky anomaly, in which I have a peak and the heat capacity drops again. And this measurement of the heat capacity can actually tell me what the value of the exchange coupling constant J is for the system. So all thermodynamical variables originate from a calculation of the partition function. And one kind of interaction that we studied here, the Ising interaction, can lead to different kinds of magnetic behavior. In fact, for an Ising 1D chain, we cannot have ferromagnetism because the critical temperature is 0 kelvins. Now we would like to talk about band magnetism, but before that we have to talk about bands. So what I would like to do in the remainder of this course, in at least some portion of the remainder of this course, is, of course, I would like to talk about band magnetism. For that, I would need a model which is not a means field model, but is a model based upon interactions. And the model that I would like to introduce is the Hubbard model, or the Hubbard interaction. Through the Hubbard interaction, I will talk about the Stoner model. That is a good description of band magnetism. But in order to talk about the Hubbard interaction, I have to talk about the tin muffin model or the tight binding model. The tight binding Hamiltonian. So I will have to talk about the tight binding Hamiltonian in chains of atoms in 1D lattices. But it's easier to start talking about tight binding inside a molecule. So this is the scheme of affairs that I would like to follow in this lecture and the next lecture. So today I would like to talk about tight binding inside a molecule, and I will go through it fast because we've already seen this. Suppose we've seen this in some variant. For example, suppose I have a hydrogen molecule, 2 nuclei, 1 electron. Now suppose my atomic orbitals are denoted as ket1 and ket2. These are my atomic orbitals. This orbital sits with nucleus 1, this orbital sits with nucleus 2. Each nucleus has just one orbital. For the time being, we're assuming that. Okay? And we also assume that the overlap between these orbitals is 0. It's not a good approximation, especially when the nuclei are close together, but let's assume for the time being that these are orthogonal orbitals. Now we can also write down the Hamiltonian for the system. The Hamiltonian for the system is just 1 electron is a kinetic energy term plus a potential energy term of the electron interacting with nucleus 1 plus a potential energy term of the nucleus interacting with electron 2 with nucleus of the electron interacting with the second nucleus. If I want to spell these down, K equals P square over 2m for the electron, V1 equals 1 over 4 pi epsilon naught minus E square, position of the electron minus the first nucleus, and V2 is with respect to the second nucleus. Okay, so this is the Hamiltonian for the system. And we also know, we also have the relationships K plus V1 when acting on ket1. This is just the atomic orbital for the first nucleus. This will just give us the ground state energy E0 for the electron, right? This is just an atomic Hamiltonian. Likewise, K plus V2 for the second orbital gives us E0. The energies of the two atomic systems are identical. It's a homonuclear system. So this is something we already know. We are given this information. Now, if those two nuclei come close together and the electron is now in the field of the two nuclei, the wave function of that electron site, suppose we form a linear combination of atomic orbitals. We propose a trial solution, and that is C1 plus C2 gets 2. We form a superposition of the two atomic orbitals. This is generally called a linear combination of atomic orbitals. This is how actually we describe covalent and ionic bonding. Okay, so we have a linear combination of atomic orbitals. Now we would like to write down the time-independent Schrodinger equation. And we would like to find out what these coefficients are going to be. And we would like to find out the ground state of the system. Okay? So if we look at the Schrodinger equation, its time-independent form, it can be written, one way of writing the Schrodinger equation is through this, H, M, N, which is some element in the Hamiltonian. So this is some element multiplied with Cn, summed over all n's, will give you the energy times Cm. So this is one version of the Schrodinger equation. You can derive this as a homework, probably I'll give it, using, you can easily derive this, and the kind of approach that I am following here is called the variational principle. The variational technique. So what you need to do is, let me give you a hint, the energy is given by the inner product of the Hamiltonian with the trial solution. You choose any solution, trial solution side. This is the energy. You minimize this energy with respect to Cm and with respect to the complex conjugate of the coefficient Cm, you get this result. Okay, this is probably a homework question that I will give to you. Now this is my Schrodinger equation, the time independent form, and these terms inside the Hamiltonian, Hmn, are simply this inner product here. Now suppose I would like to find out the Hamiltonian expressed in the basis of the atomic orbitals, which means I would like to find out H as H11, H12, H21, H22. Now H11 for this system is atomic orbital 1, the Hamiltonian is K plus V1 plus V2, K1. This is H11. Correct? Now K plus V1, Ket1 is an eigenstate of just this part. So when this part of the Hamiltonian acts on Ket1, I get E naught Ket1. There is 1 here, so I get E naught. The ground state energy, minus 13.6 electron volts. But I have this term as well. So this is Bra1, V1, Ket1. Now this is the interaction of an electron that belongs to the first orbital to the first nucleus. V1, this is V1 here, this is Ket1. So if I were to write down the two orbitals, this is just a cartoonic picture. This is orbital 1, an electron, orbital 2, an electron that belongs to this orbital, that belongs here, is interacting with this nucleus. This is this term. V2, oh, sorry, I'm so sorry. V2. Now this is first orbital, an electron in the first orbital is interacting with the second. So this is this interaction here. Okay, so I call this term, let me give it a name. It's an energy V cross. The cross coupling of an electron with a nucleus to which it doesn't really belong. Of the electron inside the first atomic orbital being coupled to the second nucleus. So we have found out this term. Alright. Now this term will be H. Okay, let me go to this term now. So H11 is E naught plus V1, Ket Bra 1, V2, 1. This is E naught plus V cross, a cross coupling term. Likewise, H22 is going to be equal to E naught plus 2 V1 2, right? Okay. Now this is E naught. This has to be the same as V cross. This term has to be the same as this term because of symmetry concentration. Now H12, if you look at H12, this is 1, the Hamiltonian, which is K plus V1 plus V2, 2. All right. Now, what is this? What is this term going to be equal to? Why? So this term is not going to be equal to 0. See, K plus V1 2 plus 1 V2 2. This term is 0. No doubt, this term is 0 because this is E naught. And ket 1 and ket 2 are orthogonal. This term is 0. But what about this term? This is non-zero. This is like an exchange interaction. Okay? So this term is non-zero. Let's call this term T. This is some number. It's a complex number. Let's call it T. And for conventional reason, let's put a minus sign in it. Let's call this term minus T. What this term physically tells us is the probability is an amplitude of transfer of the electron from one orbital to the other. It couples orbital 2 to orbital 1. So the electron can make a hop or it can tunnel from one orbital to the other orbital. Okay? And I will explain this further in a minute in a better manner. So this is minus T. Likewise, H21. Since the Hamiltonian is Hermitian, this has to be equal to minus T star. So the Hamiltonian for the system in the basis of the atomic orbitals, in the ket 1, ket 2 basis, is given by E naught plus V cross minus T star E naught plus V cross. Now this Hamiltonian can give me the evolution of the complex coefficients inside my trial solution. Okay. Now I see that if I multiply this, if I perform this multiplication, which is the left hand side of the Schrodinger equation, then this term, if I start off with C1 1 and C2 0, if the system evolves under the action of this Hamiltonian according to the time dependent Schrodinger equation, ket 1 will go into ket 2, which means that the electron can change its orbital. So take this Hamiltonian, exponentiate this, that is, have this input state and find out the evolution of this state with time. You will get some ket 2 as well. The system will oscillate into ket 2, which means that the presence of this off-diagonal term is creating a hopping from orbital 1 to orbital 2. So it's called a hopping term, or a transfer term, or a coupling term. This kind of Hamiltonian is called the tight binding Hamiltonian because we assume that each orbital is tightly bound to its nucleus. Now if we look at the Hamiltonian, the tight binding Hamiltonian, we can diagonalize it to find the eigenstates. There are two possible eigenstates. Okay, if this is minus T and T is taken to be positive, okay, then one eigenstate, let's label it phi 1, is 1 over under root 2, 1 plus ket 1 plus ket 2. This is one eigenstate for the Hamiltonian. The other eigenstate is So we have two eigenstates here. This is a linear combination of atomic orbitals with precise values of these coefficients. Each one of them is 1 over under root 2. Here, this is 1 over under root 2, this is minus 1 over under root 2. These are the two eigenstates of the system for the hydrogen plus molecule. Now these are called molecular orbitals. Okay, and they must have certain energy. The energy can be found out by diagonalizing this matrix. So the eigenvalues for this system, remember it's a Pauli sigma x matrix. So the eigenvalues of this particular state are E naught plus V cross minus T modulus squared. इसका eigenvalue sigma x की एक eigenvalue होगी +1, एक -1, right? So we have these off diagonal terms. So one is going to be plus T modulus square, other is going to be minus T modulus square. So this state is of the lower energy. The other eigenvalue is going to be E naught plus V cross plus T modulus square. This orbital, this wave function is called a bonding molecular orbital. It's lower in energy. This is called an antibonding molecular orbital. So the type binding Hamiltonian gives us these two covalent bonds. Okay? I can plot these orbitals, the energies of these orbitals, with respect to distance between the nuclei. Let me call this R. The distance between the two nuclei, or capital R, is R2 minus R1. Now this function T, this number T is a hopping integral, it's a hopping number. It depends upon the distance between the nuclei. If the nuclei is far apart, T is small. T is really small, almost zero. When the nuclei come close together, T increases. So T depends upon the distance between the nuclei. It exponentially depends upon the distance between the nuclei. So when you're far away, when this distance is large, T is 0, the two states are degenerate. And when the two states are degenerate, the eigenstates will turn out to be ket 1 and ket 2. If this is 0, the eigenstates are merely ket 1 and ket 2. They are the atomic orbitals. You have two independent atoms. Now, if you bring the atoms close together, T goes up, which means that these become the eigenstates. And the energies of these states, for the bonding orbital, it goes up. For the antibonding, this goes up because of this plus sign. This is going up as T is reduced. As the distance is reduced, T goes up, so this goes up. For this particular state, if you find out the energies, it goes down, down, but practically after a certain point it starts going up. Because when the two nuclei are close together, repulsion between the nuclei also kicks in, and that is not included in the model over there. So this is the energy for the bonding molecular orbital. This is the energy for the anti-bonding molecular orbital. And if you have a single electron inside the molecule, it has to go into the bonding molecular orbital. If you have two electrons, both of them with opposite spins will go into the bonding molecular orbital and you will form a hydrogen molecule. So when the overlap between the nuclei decreases, the hopping parameter goes up. And when the hopping parameter is large, so hopping goes up in this direction. which means that the electron can oscillate between the two orbitals, between the two nucleotides, spend sometimes the first nucleus, sometimes the second nucleus. So a covalent bond is formed. So this tight binding model describes that a covalent bond can be formed. So this is a tight binding molecule for a molecule. And now what we would like to do, we would like to take one step further and now talk about a chain of spins, which and we would like to find out how those chain of atoms and they are interacting through this tight binding Hamiltonian. So now we would like to talk, probably we will not be able to finish this today, but let me set up the problem at least. We'd like to talk about a tight binding chain. Alright. You see, as the distance goes down, these energy levels change. Now, when we talk about chains of atoms, there is the possibility that these energy levels change in such a way that bands are formed. So now I am actually giving you a lecture on condensed matter physics. I am telling you how bands are formed through the tight binding model. So suppose I have a chain of atoms, long chain of atoms, a lattice, a 1D lattice, 1 point for 1 atom per lattice point, and the separation is A. And there is, associated with each atom, I suppose there is only one orbital. One orbital per atom. And my unit cell is this. There is 1 point per unit cell. One orbital per lattice point, or one orbital per atom, and one electron per orbital. That's my statement. Okay? You know you can have diatomic lattices as well, but this is a monatomic lattice. One atom per unit cell of one kind, and there is one orbital and one electron belonging to that orbital. And the orbitals I am labeling as ket m. So this is ket 1, ket 2, ket 3, and so on. Now if I write the Hamiltonian for a single electron, one electron, it's going to be the kinetic energy of that electron plus the interaction of the electron with any nucleus inside the chain. Okay? So plus some Vj, the interaction with the jth nucleus, sum over all j's. Okay, so this is the Hamiltonian for a single electron. Alright, so I think I'll set up the problem here. It's a good to stop at the Hamiltonian. There's some logistics that has to be dealt with. So inshallah I'll see you on Monday, and I'm going to post the homework on this weekend. Thank you very much.